Hi there. Welcome to RigDandy. This is a project done by myself for CIS 660. So our goals and objectives, this kind of changed. Our original objective was to develop a sort of full rigging system, but what ended up happening, because I was doing research and sort of developing a product at the same time, is to develop an easy way to compare different pieces of research code, have a common interfaces to make it easy to plug in different pieces of code. So, like, let's say I have something in C, but I also have something in MATLAB. There should be some common high-level interface so I can plug both in and compare them, so they would be next to each other. I think that sort of the main problem here is that I wanted to tie my research into 660, but the research just didn't end up getting far enough. So we kind of had to change midway, and we kind of ended up with a strange, I don't know if you can call it a tool so much as it is a thing that lets you compare sort of two different algorithms. Technical approach is mostly based on my own research this year. It's most closely related to locally injective mappings. It's really about sort of deforming a bar, getting some kind of skinning to work on a bar, but avoiding things like self-collisions and bulging. And I use a lot of hacks also to get MATLAB and Maya coupled. So results. Well, here you can see this bar is being bent with standard skinning. This bar is being bent with our algorithm. Our algorithm avoids a bulge. And this is the bar at rest shape. We can bend, if we change the time, I tied it to time, so one thing you can do is that you can sort of render out to video. You can see this is the bar at 40. This is the old algorithm at 45 degrees. This is the new algorithm at 45 degrees. You go up to a high number like 135, then there's MATLAB going. Then you'll see more of a difference. As you can see, here we have some self-intersection in this region. Here we avoid the self-intersection, instead we have a nice contact. And sort of this allows us to compare both. This is the rest shape. What you can do actually is we can go to vertex mode, and we can sort of bend. We can edit the shape, and you can see that this is reflected in our standard skinning example, but not yet in our MATLAB example. This shape was generated through the binding to MATLAB, because that sort of makes some assumptions on what the input mesh is, and unfortunately those were hard to get around. So the cool thing that I can do though is I've also developed a script which sort of automatically takes pictures of the shapes at different angles. So hopefully this will run. And what it does is that it moves the camera, and it basically takes pictures of the viewport. And what we get as a final result is sort of this sequence of pictures which shows our bar at 45, 90, 135, 45, 90, 135. And this is the rest shape, so they're all the same, but using different algorithms. So this is nice because, you know, with my research code sort of before, I had to sort of take pictures of each manually by hand. But, you know, if you use Maya, you can zoom in, you can have the camera do the optimal zoom for you, and then you can get this nice sequence of images out. So that's fairly nice. Yeah, the last thing that I want to point out is the code. Although there are some hacks specific to the MATLAB thing, because it was just hard to bind to Maya, like there are some nice common principles. For example, this function is used to calculate the skinned mesh. Doesn't matter which algorithm you use or which code or which language you bind to, it's all wrapped by this. And sort of depending on which one we're using, we instantiate different subclasses of this solver class. And because we have polymorphism, we can always calculate the skin to mesh. So that's what I mean by common interface. Something that Dr. Lane thought would be useful is a common code interface that would make it easy to plug in new things. Because now if you plug in something new, you just call you just make a wrapper, you make an interface that looks like calc skin mesh, and you give it an input mesh and an output mesh. And if you did it right, you should be able to compare that one next to the two that already exist, the two that we're already comparing.